According to the principles of reliability engineering, maintenance is actions necessary to ensure that a physical asset does what its user wants it to do. You jump in your car, you start it up, and it starts. That physical asset is doing what you want it to do. If it doesn't start, it's failed. And what's the definition of a failure? The inability of a physical asset to do what its user wants it to do. And that's it. That's an RCM process. They've actually defined what maintenance is and what a failure is. There's reactive maintenance. Not really, not good, but it actually does have its place. Let's suppose we have two pumps on a cooling, I don't know, say a nuclear reactor for argument's sake. If this pump here fails, this one can kick in. That's actually reactive maintenance. This is actually the protective device, and the protective function is pumping cooling water. Unfortunately, we talked about the tire. If you had to change that tire, that's reactive maintenance. Changing a light bulb is reactive maintenance. Now, do we really want to put something in place that we want to monitor the condition of a light bulb? Does it have safety or environmental consequences? No, it probably just has like some minor, economic consequences. Reactive maintenance, not good, but it does have its place. Then we have preventive maintenance. Preventive maintenance, as John was mentioning earlier, is generally is done by elapsed time and running time. Elapsed time could be something which is like, every week or so we perform this, or running time is we have a meter on a machine, and after it's done so many thousand hours or whatever, we do some preventive maintenance. And the idea with preventive maintenance is to prevent catastrophic failure or a complete functional loss. Then we have predictive maintenance. This is known as condition monitor or on condition. This is where, and it doesn't necessarily have to mean that we're putting these complicated devices on there like accelerometers that measure vibration analysis and stuff like that. It's actually a lot more simple, where you can actually just use like historical data, reading pressure gauges, flow temperatures, differential pressure temperatures. It's not necessarily has to be high tech like thermography or whatever. I want to try and get things real simple with TPM. I don't want to complicate it. I just demonstrate to you how simple really maintenance is, the actual definition of it. So we have predictive maintenance. And this is the most important type of maintenance we can do. Maintenance-free design. This, I'm going to put so many asterisks next to this because this is so very, very important. Because if we have to do maintenance to any physical asset, it's fundamentally a failure in design engineering. And it's as common a law as the law of gravity. This is very, very important. Dave, when was the last time you checked the electrolyte on your battery in your car?
Well, you don't do that anymore.
Right.
I was just thinking of the television. You don't do maintenance on your television at home anymore.
Yeah, that's right. If I buy a physical asset, how much does it cost today? Like $20,000, $15,000? I don't want to spend money having it in the shop every 10,000 miles, having to decoke or whatever. So yeah, they build a better mousetrap. We do maintenance-free batteries. Another aspect of maintenance-free is information systems. Let's look at a photocopier. Get a jam in the machine. It tells you that it has a jam. It tells you where it is, and then it tells you how to unjam it. Open door A, go in part B, remove the jam. Back in the 60s, when Rank Zeros first started their, photocopiers, they had to go, we have a paper jam, you send in a technician. That's how it really was. So they had to call in a technician to get the paper jam out. So these are the types of maintenance. Reactive, not necessarily good, but it has its place. Preventive maintenance, predictive, and maintenance-free. What is TPM? TPM is actually a best practice. What's a best practice? Actions necessary to have the highest productivity at the lowest cost. And best practice has its roots in continuous improvement. Ensuring that how things are done today is not necessarily going to be a repetition of how things are done tomorrow. TPM, the definition of TPM. Well, TPM is actually a merger of two cultures. American practices of preventive maintenance, because the Americans invented this thing called preventive maintenance. Before that, it was just reactive. And it actually had its start in the aviation industry. They had so many planes falling out of the sky that we'd have to do something about these engines failing and the death rate. What about this thing? What about we do this thing called preventive maintenance? We'd like practically in there. And they actually did too much maintenance. Then they had this early infant mortality rate. So they actually came eventually to this line, what we call that bathtub curve, of doing preventive maintenance. So it's a merger of two cultures, American practices of preventive maintenance and the Japanese concepts of total quality control and total employee involvement. And just like Kaizen, it begins and ends with people. And what you're doing is you're giving people the tools to plan, control, and continuously improve their work processes. So it's a merger of American practices of preventive maintenance, Japanese concepts of total quality control, and total employee involvement. And what you have is a very innovative system for equipment maintenance that eliminates breakdowns, improves its effectiveness, or OEE, the overall equipment effectiveness, through availability, through quality, and through performance. And it has to be done with autonomous maintenance for operators. This early part of this, why is we have such high failure rate? What do we think that? Because what would be like to say the cause of that? I can demonstrate one right here.
You're talking in the initial phase, Fred?
Yeah.
Defective components.
Poor design.
Yeah.
You guys recognize this?
Yes.
What do you think's wrong with that valve? It's got way too many parts. And this one here, I mean that one there, and this one's right. Oh my God. Dude, I think that's got like 10 parts. This.
Send it down here, Fred.
This one here, I don't know, 4 parts to it. Spring. It's the same valve, you know, an inlet check valve. So, product design. So the cause of that is poor design. Over-engineered. Over-engineered. You could classify that. Over-engineering. Yeah. So poor design for this, okay, poor design of the product. Also poor design of the actual machine itself. I do digress a lot, but one of the things I'm going to say here, one of the things you didn't do very well at Artline that you had the greatest opportunity to do is we really didn't form, you know, the first, 5 stages of TPM is actually like the preparational stage, step 6, of course, is the kickoff. We didn't form a committee. And you must have a representative from your engineering department, for your maintenance and operations. And we didn't do that very well because there's a wealth of talent and information out there that people can have that input to like, well, I don't think that would be a good idea because we've had that problem with that cylinder before. Okay, we'll use a different type of cylinder. We didn't really do that. And unfortunately, John, on the tank valve side of our plant, reactive maintenance.
Yeah, sure.
Okay. So poor design, the category there. Okay, so